Alright, this video is intended to help you with your law of universal gravitation homework problems. I know sometimes when you have a new unit and a new equation, it can be tricky to figure out how to read the word problems and how to figure out what is this telling me and what else do I need and what am I trying to find. So the first three problems were done for you in a previous video, so I will be starting with question number 4. Question 4 says, how much would your 20-kilogram dog weigh on Neptune? Now, right away, you know that you have a mass. You can call it mass 1. It doesn't matter if you call it mass 1 or mass 2, just as long as you keep them separate. So you have mass 1, your dog, which is 20 kilograms. And you have a planet, Neptune. So you're going to have the mass of Neptune for your mass 2. And the mass of Neptune is 1.03 times 10 to the 26th kilogram. You get that from the top of your worksheet. We also know that the distance, in this case the radius of Neptune, is 2.43 times 10 to the 7th meter. What that means is that the distance between our two objects, in this case Neptune and the dog, the distance from the center of Neptune to the center of the dog is just the radius of that planet. And what you're looking for is Fg, or the force of gravity. How do you know that's what you're looking for? Well, this right here. How much does your dog weigh? And we know from our previous unit that weight is a force. Now, to solve this problem, you have our brand new equation for universal gravitation, which is Fg, or the force of gravity, the gravitational force, is equal to big G, which is a constant. It's always the same. That's at the top of your worksheet as well, times m1 times m2 divided by d squared. The important thing here is to make sure you always square your distance. It feels really strange when we're working with these really big numbers, but always square your distance. That makes a huge difference in your final answer. Question number 5 says, which is greater, the force exerted by Saturn on the Sun or the force exerted by the Earth on the Sun? And then how much greater is it? Now, this is a two-part question. The first thing you have to do is find your Fg, your force, for Saturn and the Sun. So the mass of Saturn would be your m1, mass of the Sun would be your m2. And if you look at the top of your worksheet, you'll notice that it also gives you the distance between Saturn and the Sun. So you use that as your distance. Then your second step is going to be to find Fg, or the gravitational force, for Earth and the Sun. You'll do it exactly the same way, except for now your m1 is the mass of the Earth. And then you just compare your two answers. In order to do that, you take whichever one is smaller and subtract it from the bigger one. Find the difference. Tell me which one has a greater force, and then tell me how much greater is that force. Number 6. A distance of 2 meters separates two objects of equal mass. If the gravitational force between them is 2.6 times 10 to the negative 7 newtons, that's a really small force, find the mass of each object. Now we're still using our same equation. Fg equals big G times mass 1 times mass 2 divided by your distance squared. Now let's look at our problem again. It says two objects of equal mass. So mass 1 and mass 2 are the same. So what that means is that really what you have is big G times m squared divided by d squared. Okay, m1 times m2 is mass squared. Now we just need to rearrange our equation. So when you look at the equation, we want to know mass, the mass of each object. So I need mass all by itself. So what that means is I want the big G and the d squared to go away. I want them to be on the other side of the equation. I do that by flipping my fraction over and multiplying it by both sides. On the right side of the equation, the G cancels, the d squared cancels, and I'm left just with mass squared. And then on the other side, Fg times d squared divided by big G. So here's what I'm left with. But I don't want m squared. I want just one mass all by itself. So what do I have to do? I have to take the square root. And here is your final equation. M is equal to the square root of the force, which is given to you in your problem, times your distance squared, so 2 meters squared, divided by big G, which is that constant 6.67 times 10 to the negative 11. Question number 7. If the gravitational field strength at the top of Mount Everest is 9.772 newtons per kilogram, approximately how tall in meters is the mountain? Now the first thing is a reminder. Remember I told you guys through Remind, if you're signed up for a Remind, that there was an extra line at the beginning about calculating gravity on Jupiter. We're going to ignore that. That doesn't matter. That was part of an old question. We're going to focus on this, the gravitational field strength at the top of Mount Everest. So how tall is the mountain? Now it gives you this 9.772 newtons per kilogram. That's little g. That's the acceleration of gravity towards the ground at the top of Mount Everest. Notice how this is really close to the 9.8 that we've been using in class, or even the 10 that we've used for gravity on Earth. Now what this means, 9.772 newtons per kilogram, is that your force is 9.772 newtons for every mass of 1 kilogram. So you can actually take this number right here and separate it into two givens. You have a force and you have mass 1. So that brings us to our guess method, GUESS. What are our givens? Force, 9.772 newtons. Mass 1, 1 kilogram, which we got from here. Mass 2 is the mass of the Earth, because Mount Everest is a mountain on Earth. And we're looking for a D. We want to know how tall. That's a distance. So you put your equation together, and you did this one previously on number 2, I believe it was. Your distance is equal to the square root of big G times mass 1 times mass 2 divided by your force. But in this case, you're not finished, because this distance right here will tell you how far is it from the center of the Earth to the top of Mount Everest. But that's not what I want. I don't want that whole length right there. So what do you have to do? You take whatever answer you get here and you subtract the radius of the Earth that's given to you on the front of your worksheet. And what that'll tell you is that difference is how tall is Mount Everest? What's left to be the height of the mountain? Question number 8. If you dropped a ball while standing on the surface of Mars, at what rate would it accelerate toward the ground? Now here's where you have to remember a little bit about what we've done before. Okay, force of weight equals mass times gravity. Force in general is a mass times acceleration. And remember, when we use 9.8 or 10 meters per second to describe gravity, what we're really saying is 10 meters per second squared is the acceleration because of gravity. It's going toward the ground at that rate because gravity is pulling it. Because of that, we can do just sort of a general 1 kilogram mass. We can say, generally speaking, for every kilogram, what is the gravitational force? So we're going to start off with a mass of 1 kilogram. Because we're on Mars, M2, the second mass, would be the mass of Mars, 6.43 times 10 to the 23rd kilograms. Our distance here is the radius of Mars, 3.4 times 10 to the 6 meters. And to start with, what you're looking for is force, Fg. Okay? You know the equation for that. Big G times mass 1 times mass 2 divided by your distance squared. And whatever answer you get there is going to be the same as the acceleration due to gravity. You're going to take that force divided by 1 kilogram to get your meters per second squared. The number is not going to change. Really, it's just the units that'll change for your final answer. Number 9 is another one that has a couple of different steps. If a person weighs 882 newtons on the surface of the Earth, at what altitude above the Earth's surface must they be for their weight to drop to 800 newtons? So we know that on Earth, they weigh 882 newtons. As you get higher and higher up into the atmosphere and you get farther and farther away from the surface, the weight is going to drop because gravity is not pulling quite as hard on you. So again, we need to remember that weight, or the force of weight, is equal to mass times gravity. We know that on Earth, our gravity is 9.8, or we can use 10. So 882 newtons, the weight on the surface, is equal to the mass of this person times gravity, 10 meters per second squared. When you divide that, you get the mass of that actual person. So our mass 1, M1, is the mass of the person, 88.2 kilograms. And we know that our force, our gravitational force, is 800 newtons. That's our goal. I want to know, where do I need to be to have a weight of 800 newtons? And we have our mass 2. Our second object is the Earth, because we're talking about how far away from the Earth's surface. And our mass 2 is 5.98 times 10 to the 24 kilograms. We're looking for a distance, once again, square root of big G times M1 times M2 divided by force. When you plug all that into the calculator, you're going to get some big number. What that number is telling you is the distance from the center of the Earth to the center of the person. But that's not what I want. I don't care about the Earth itself. I just want to know the part that's above the Earth's surface. So just like we did before, you're going to take that answer, subtract the radius of the Earth, again from the front of your worksheet, and whatever's left over is going to be your altitude above the surface. How far away from the surface of the Earth do you have to be? Question number 10 is very, very straightforward. If a 50 kilogram mass weighs 554 newtons on the planet Saturn, calculate Saturn's radius. So we have mass 1, 50 kilograms. Mass 2 is the mass of Saturn, 5.68 times 10 to the 26 kilograms. We know that our force, or our weight, is 554 newtons. And you're looking for a distance. Once again, square root of big G times M1 times M2 divided by your force. Make sure, you guys, that you're doing the square root part so often. You do all of the underneath part and you get a beautiful answer, and then you just don't finish. You're not quite there. You can't stop until you take the square root. It's really, really important, so don't forget that step. And finally, number 11. If a boy has a mass of 60 kilograms and a girl has a mass of 50 kilograms, what is the gravitational force of attraction if they are standing 3 meters apart? It sounds kind of silly and made up, but here's the deal. Everything has gravity. Everything attracts everything else. It's a really, really small amount, as we're going to see here in just a minute, but everything attracts everything else. Even me to the person standing next to me, and you to the person standing next to you. There's a gravitational force between them. So let's figure this problem out. This one's also fairly straightforward. M1, the boy, 60 kilograms. M2 is the girl, which is 50 kilograms. You know that the distance between them is 3 meters, and you are looking for the force, gravitational force. So we go back to our old standard equation, big G times M1 times M2 divided by the distance squared. And that's the gravitational force of attraction between those two people. When you plug that into your calculator, you'll see it's very, very small. Hopefully that's been helpful. Make sure and ask your teacher if you have any more questions.